Okay, here we have another interesting example, which is also a very important example. Uh, this example is that of a simple oscillator and introduces the concept of phonons. Again, it's an application of quantum mechanics or Schrödinger equation. And if you remember from your classical mechanics, this is a very famous problem that we have here. And this problem is that of the oscillator, which is the uh, harmonic oscillator, what we call the harmonic oscillator. And it's a very important problem indeed. And we're going to do quantum mechanics formulation of this problem. Okay, let's first talk about classical mechanics in terms of this problem, the simple oscillator. In classical mechanics, we have a mass m, okay, here, and then we have a spring. This spring has a spring constant, which is k sub s. And at the beginning, the mass is located at position x0. So we start measuring the position from this point, x0. And then at t equals 0, at the beginning, the mass is given a displacement, arbitrary x, and then released from rest. So what happens is there would be a restoring force trying to restore the mass back to its original position, so the direction of the force will be from right to left. And this force, F, is the spring constant K sub S times X. This minus sign indicates that the force is directed in the opposite direction of the x-axis, that is in the negative x direction. So this is the problem. And here, this equation F equals minus Ks is the classical force equation or the force equation. So if we want to solve this oscillator or harmonic oscillator problem, and if we want to solve it classically, then we can use Newton's second law. The harmonic oscillator problem or model is very important because if we can solve it quantum mechanically, it describes oscillations and therefore it can describe electromagnetic radiation as well as any other oscillations like thermal oscillations or vibrations of atoms in a solid, which is also very important. So let us try, first of all, remind ourselves with the classical approach. We know that the force F is a restoring force, and this force is directed in the negative x direction, and it depends on the spring constant Ks and the displacement x at any time, at any position. So from Newton's second law, mass times acceleration, here is the mass, times the acceleration, which is d squared x by dt squared, is equal to the force, which is minus ksx. So this is the classical equation of motion. Now, we know that this is a very famous differential equation, second order differential equation, and we can try a solution of this sort. X equals a constant A times E exponential I omega t plus another constant B, e minus I omega t. So this gives us oscillations. It's sine cosine oscillations. And we have frequency, angular frequency omega for this oscillation. And this angular frequency omega for the oscillation is given by the square root of Ks, which is the spring constant divided by m. So it's a very simple exercise. You can try this equation, this function x back in this differential equation, and you can immediately see that it satisfies the differential equation, provided that the frequency, angular frequency omega, is equal to the square root of Ks over m. So this is the classical picture. We know that the values of energy are greater than or equal to zero, or classically, any energy greater than or equal to greater than zero is actually allowed for the oscillator. So this is the classical picture, and the outcome is oscillations. Now, let us try to approach this problem using quantum mechanics. So let us look at the quantum mechanical solution. The first thing we need to do, if we are to use Schrödinger equation, is to find the potential. And the potential of the force u of x at any position x is actually equal to the integral from 0 to an arbitrary x of f of x d of x. Here I'm using x dash and dx dash because these are only dummy variables. And then the final potential function is going to be a function of x, which is the position variable. So, having obtained the potential u of x, now I have to go to Schrödinger equation, and let me just remind you of Schrödinger equation. It is h bar squared divided by 2m, and then delta squared, it's psi, by delta x squared, okay, time plus e minus u, which is u of x in this case here. It's a function of x, u of x, and it's one-dimensional problem, u of x, function of x, times psi, and this is equal to 0. Since I'm doing this problem in one dimension, only the x-axis, then I don't need to use partial derivatives. I can use complete derivatives. So this equation, and if we use this potential here for u of x, then this equation reduces to this equation here, where alpha is equal to 2me over h bar squared, and beta squared is equal to km over h bar squared. So this is my equation, and this is what I need to solve. If I solve this equation, what I will get is the energy of these oscillations. Okay, that is what I get out of this. In terms of the mass of the object, and in terms of k, which is the spring constant. Now, I'm not going to go in details through this solution. You can look at the notes here, and you can immediately see that we have the whole process of solving this second order differential equation, and we do that by choosing a polynomial solution f of x times an exponential function e minus beta over beta x squared over 2. So if we try this type of solution, we can claim that this psi of x solves this differential equation. And if it solves this differential equation, then what I need to do is substitute this psi of x back in the differential equation. And if we differentiate this psi of x into the differential equation, this is the resulting differential equation that we come up with. Now, why do we do this? Because now our differential equation is homogeneous, okay, and it's of second order, right? Differential equation, right? So that the functions here, right, you can clearly see that, we have a homogeneous differential equation, which is again second order, and we have to solve it. How do we solve it? Right? Now, again, here we have the function f, so the differential equation, the Schrodinger equation, becomes an equation in this function f. Okay? So now, what we do, again, I'm just outlining the solution, use y, change the variable x to a variable y, which is equal beta to power half x, and then use h of y instead of f of x. So what I did is I changed the independent variable x to another independent variable y, and beta is a constant, as we know, so that doesn't change the independent variability much. However, it makes the equation more compact and easier. Okay, so the differential equation becomes a differential equation in H. Now, to solve this differential equation, we're going to use a polynomial h of y, and this polynomial of order m, where m here is on top, and a sub n are the coefficients of y to power n. And so we can use this polynomial h of y, and applying this polynomial to this differential equation here gives us the recursion formula, which relates the coefficient n plus 2 to the coefficient a sub n. As I said, I'm not interested here in the math of solving the differential equation. So what I'm interested in, so I'm just outlining how to solve the differential equations here. You could go and consult any partial differential equations or differential equation textbook and see how we can solve a differential equation of this type and how we can obtain this recursion formula. But if you go ahead and complete the solution, we find that the energy of oscillations, E, is again quantized. It follows integral values of n. The energy of the nth state, or the state number n, is equal to n plus half times h bar times the square root of ksm. Remember, this square root ksm is omega, the frequency of oscillation as we obtained it in the classical solution. So we can use that here and write the energy of oscillations for this object or for this mass is quantized according to quantum mechanics. The energy of this mass can only take discrete values, separated values. These values depend on a quantum number n, which takes the values 0, 1, 2, 3, 4, 5, etc. So each one of these is a quantum energy state, and the energy is quantized. Now, this quantum energy state is what we call the photon. Remember, the photon has energy of the form h bar omega. So what we have here are bundles of energy in the form of photons. So that's why we said at the beginning, this simple harmonic oscillator problem, when we treat it quantum mechanically, it can tell us about our hypothesis, or our first hypothesis at the beginning of this chapter, when we talked about the energy of a photon of electromagnetic radiation as h bar times some frequency omega. Now, here we have different excited states for these energies of oscillator. Also, if we have vibrations of atoms in a crystal or in a solid, again, these vibrations of atoms can be described in terms of oscillations. These oscillations are also have energies of the form n plus half h bar omega. Now, each one of these vibrational oscillations is called phonon. So, oscillations of a crystal are called phonons. And the energy of the phonons are of the form h bar omega, just like the same format at the energy of the photons. Again, phonons are looked at as oscillations. So this is another problem which we can solve using quantum mechanics. Now, there is another important problem, and let me load the file now for that problem. And it's a very very important problem that we encounter so much in all our understanding, of chemistry and our understanding of physics. And that important problem is that of atom. How do we understand atoms? What are the atoms like? So let me go back and then overview this second example, which is a very important example. This example is the electronic structure of atoms. Again, we can look at this using Schrödinger equation. Now, I'm going again to overview quickly this, and I'll leave you to go through it, to go through all the derivations yourself. But in an atom, we have studied in chemistry that atoms would have electrons. And if we take a simple atom, okay, if we take an atom that has only one electron, okay, so that one electron would have a charge, which is, the charge would be minus 1.6 times 10 to minus 19 coulomb. In an atom, okay, we have a nucleus, which is positive charge, and then we have an electron, which is a negative charge, and this electron has a negative charge minus 1.6 times 10 to minus 19. the nucleus would have a positive charge, which is Z times E. Z is the atomic number. Okay, so Z is the atomic number defined as the number of protons in the nucleus. So such a problem is called problem of a hydrogenic atom. When we have only one electron, that is as if we're talking about hydrogen, because hydrogen has only one electron. And also hydrogen, the most abundant isotope of hydrogen, has one, or hydrogen, all hydrogen have one proton. But then different isotopes of hydrogen will have different neutrons. But in a hydrogen atom, we have one electron, one proton. So Z in a hydrogen atom is equal to 1. So that's a famous problem. We can solve it using quantum mechanics. Why am I saying that? Because there is a Coulombic force between this electron and the nucleus, or the proton in the nucleus. This force is the Coulombic force. And I can obtain the Coulombic potential associated with this Coulombic force. And once one obtains the Coulombic potential, then one can use Schrödinger equation. Okay, so that is the overall picture. So I'm going to skip all this and look here and formulate the problem. We have a charge Q1 and another charge Q2. They're separated by a distance S. So the potential, that's what we learned from electricity and magnetism, the force is equal to the product of the two charges divided by the separation squared times a constant K. And this constant K is actually 4 pi times epsilon naught. Epsilon naught is the permittivity of free space. And so this constant K is equal to 9 times 10 to 9 Newton meter squared per coulomb. And the permittivity of free space, epsilon naught, that I have used here is 8.85 times 10 to minus 12 coulomb squared per Newton per meter squared. So now I can use F and find the potential by simply taking F ds and integrating from a very far distance where this Coulombic force is inactive, and that is infinity, to some given point R. And so the potential, as we learned, goes as K Q1 Q2 over R. So the potential of a Coulombic force depends on the separation as 1 over R. And so I can use this potential now, okay, and I can use Schrödinger equation, okay. Since I have the potential of the function of R is three-dimensional, so I cannot use only the one-dimensional Schrödinger equation. I have to use the three-dimensional Schrödinger equation. Also, there is a proton involved. The mass of the proton is 1.673 times 10 to minus 27 kilogram. Okay, so the proton has a high mass. Also, the nucleus could have a neutron, which is 1.675 times 10 to minus 27. Okay, which is again, similar to that of the proton, right? But both of them are much heavier than the electron mass. The electron mass is 9.11 times 10 to minus 31. So, using the potential, okay, Okay, here are the different isotopes of hydrogen depending on variable numbers of neutrons in the nucleus. Always the proton is one in the nucleus, but we have different neutrons. That does not, the difference in neutrons, number of neutrons, does not affect the Coulombic force because neutrons are neutral. So the Coulombic force will only depend on one proton and one electron. So U of r is 1 over r, and if I plot 1 over r, it goes like this dotted plot here. And it's negative, right? Because the potential of a negative charge, which is the electron in this case, attracted by a positive nucleus, is negative. So now I'm not going to talk about Bohr model. I'm going to leave this for you to read, but I'm going to go straight to Schrödinger equation. Now, instead of using delta squared epsilon by delta x squared in the Schrödinger equation, okay, what I'm going to use, because this is a function of r, and the atom is like a sphere, so I have a three-dimensional problem. So the one-dimensional representation of Schrödinger equation will go to Nabla squared, which is the three-dimensional representation of Schrödinger equation. So Nabla squared is that operator in three dimensions, which is the derivative operator. So my equation will be Nabla squared, and here of course you have the function epsilon, and here also you have the function epsilon, and your function epsilon is a function of r, where r is the position. So your Schrödinger equation now, this is the energy here of the electron, and this is the Schrödinger equation describing an electron in hydrogen atom. Now, this is a very involved problem, and I don't want to go through the solution of this problem, but I will go straight. Actually, the way to solve it is to use spherical coordinates. But what happens, the outcome, is that the energy of the electron in an atom is quantized, and it's characterized by an integer n. This integer n is called the principal quantum number. And this n takes the values 1, 2, 3, 4, etc. So this is the principal quantum number, and it gives us the energy of the electron. Actually, these n's are, if we have the nucleus here, then we have different shells. N equals 1, n equals 2, n equals 3. Each shell is defined by n. This is n1, this is n2, this is n equals 3, and these are the atomic shells, energy shells. They are defined by this quantum number. Also, we find another number, which is quantum number L, okay? And it takes the values 0, 1, 2, 3 up to n minus 1. And this quantum number is called the orbital angular momentum quantum number. And then there is a third quantum number, m, which is called the magnetic quantum number. And it gives us the component of the angular momentum along the z direction. So in the hydrogen atom, we have a quantum number n for the shells, the energy shells, which give us the energy. And then we have a quantum number L, which gives us the angular momentum here. And then we have a quantum number M, which is called the magnetic quantum number, which gives us the component or the projection of the angular momentum along the z-axis or axis of quantization. So even the atom, which we studied in chemistry as early as high school, and we were told the story of the atom and how the energy is distributed in an atom, we're told this story by not solving any equation, Schrodinger equation or any other equation. We're told about this as experiments in chemistry and in physics tell us, but now we can see that we can actually solve Schrodinger equation or the quantum mechanics equation and get the energy shells in an atom. And these energy shells again are allowed states, separated energy states, right? Like we see here, this is an energy state, this is an energy state, this is an energy state. Each energy state is called a shell, atomic shell. In between, the energies in between are forbidden. So the electron can only be in these energy shells. And it can have certain angular momentum values, okay? And a certain values for the projection of the angular momentum. So this is, I mean, without really spending so much time looking at the details of how this problem is solved, and in fact, it's a very, very long solution, we can clearly see that we can derive the atomic structure in terms of energy and angular momentum directly from Schrodinger equation. So, in summary, we've done several examples of applying Schrodinger equation. We have applied it to a potential barrier, and that gave rise to tunneling of electrons as we described it. And then we applied it to the quantum well, and that gave rise to electromagnetic radiation emission. We also applied it to oscillations of a mass connected to a spring, and that gave us some insight or some understanding of photons and maybe phonons, which are the thermal vibrations or thermal oscillations of nuclei or atoms in a crystal. And then we also applied it to a more complex problem, which is the hydrogen atom. And we've seen that once we solve for the energy of the electron becomes quantized in what we call the electronic shells. And each electronic shell has an energy that is characterized by a quantum number n, which is called the principal quantum number, and it is actually the number for the shell. And we also saw that the angular momentum of the electron, as it is residing in a given shell, is also quantized and has certain values, as well as the projection of the angular momentum along the axis of quantization. So this concludes our very brief introduction to quantum mechanics and the Schrodinger equation and its application for some certain problems. In the next class, we will be talking about a major application which is very important to so many areas and which is very critical to so many applications. But for now, we will stop at this point.